let's take a little bit of a look at the history of the movement of the plates. We're going to switch gears here a little bit and think about maybe what the future might hold. When people first started to put together the idea of continental drift, they went out and they looked for pieces of ancient crust. Those pieces of ancient crust, shown in purple here, are called cratons. So if we take the dates of all these purple pieces and take the dates of these other pieces, which are actually Pre-Cambrian crust, okay, so older than 550 million years old, and this is modern crust, we can kind of assemble them back together in a kind of jigsaw puzzle-like way and get some idea of where the continents once were and where they might be heading in the future. About 250 million years ago, using this technique and other techniques for putting the jigsaw puzzle pieces back together, the continent of, or the supercontinent, because it's composed of many continents, of Pangaea was formed 250 million years ago. This is the one originally proposed by Wegener, the continent, the supercontinent of Pangaea. It was made up of two sort of sub-supercontinents, if you want to call them that, Laurasia and Gondwana, and those details aren't really important, but you can see that Laurasia was made up of North America and Asia, and Gondwana was made up of South America, Africa, Australia, India, and Antarctica. And here we have an early ocean, the Tethys Sea. Again, this was the picture 250 million years ago. Surrounding all of this was an ocean called Panthalassa, and these are historical details, not things you necessarily need to remember. If we go march ahead a little bit, 135 million years ago, the continents began to spread apart. And as they began to spread apart, the Tethys Sea began to close. Here we have, as Laurasia separates from Gondwana, the formation of the Atlantic Ocean Basin. So 135 million years ago, the Atlantic Basin began to form. Stepping ahead a little bit further, this is what the positions of the continents looked like 65 million years ago. Here we have the Tethys Sea pretty much closed up. And what sea do we find in that area today? The Mediterranean Sea, the Eurasian Mediterranean Sea. It's really a remnant of the Tethys Sea. One thing you may notice too is that at this time, 65 million years ago, North America and South America were not yet connected. There was no land bridge between these two, so water flowed freely from the Caribbean to the Pacific Ocean at this time. Today, we see the land bridges there, we see the positions of the modern continents, we can see where they're moving today, but it's extraordinary to think that throughout the history of our planet, at least the last 250 million years as shown here, the continents have moved apart. And all during that time, organisms living on one continent or the other either had to get on to one continent or the other or be left behind. As mountain ranges formed and other kinds of continental processes occurred, it drove the evolution of organisms. In fact, there's some thought that as this mountain range got kicked up here in Africa, it created a drying out of the interior of Africa, and it was one of the motivating forces for humans to move out of Africa and into Asia. So things like climate change, things like evolution of organisms, and even our own history, the modern history of humans, has some roots in the drifting of the continents, the movements of the continents, and the theory of plate tectonics. Well, in the 1990s, some people started thinking about, well, what happened before 250 million years? That's a lot of history that we haven't explained if we're only starting with 250 million years ago. Can we step it back further? And so, if we look at Earth between 500 and 750 million years ago, and again, using those cratons and using other pieces of evidence for putting together this jigsaw puzzle piece, we had, 750 million years ago, the supercontinent called Rodinia. So we're starting to march back further in time. And if you had been visiting our planet 750 million years ago, this is what you would see. An East Antarctica and Australia combined, a completely separate India, nearly unrecognizable Eurasia and North America. Here, this looks like the beginnings of Africa, Amazonia, the beginnings of South America, pieces of Siberia out here. Much different. It's as if you took the modern Earth as if it were an egg and just threw it on the ground and it kind of splatted apart. The supercontinent of Rodinia. Well, in 1996, University of North Carolina geologist John Rogers said, let's go even further back. And he proposed really a wonderful supercontinent called Don't you just love saying that? The supercontinent of It sounds like the supercontinent, and it sounds like the original supercontinent. And here's what it looked like. 3 billion years ago, there wasn't much continent on the Earth. In fact, there's some idea that continents, or continental crust, is really just kind of a rebaked version of oceanic crust. The very first crust on Earth was just basalt, was that oceanic crust. And as it kind of reworked and got rebaked and recooled, it made the lighter form of crust, which was the continental crust. And if we march forward using Dr. Rogers' methods, we go to 1.5 billion years ago, 2 billion years ago, 1 billion years ago, the supercontinent Rodinia, 250 to 300 million years ago, Pangaea, and the current position of the continents. This is what Rogers calls the supercontinent cycle. So that through time, we have formation of more continents. The continents exchange rocks with each other. And this is what I like to call the slow dance of the continents. Let's take a look at it one more time. Antarctica. Arctica, Baltica, and Atlantica. Rodinia. Pangaea. And our modern continents. It's kind of a nice dance. Well, if you're interested in learning more about this, there are tons of stuff on the internet about plate tectonics, about the positions of the continents, about all the wonderful things that plate tectonics does for our lives. You can check out the exploration activity in the back of the chapter in 3.1. Take a look at the course, the textbook website, and if you get a chance to watch this video, The Living Machine, it's really a classic, and it's kind of an older video. Has some things in it that aren't quite up to date, but in terms of its animated illustrations of the plate boundaries, it will really help you visualize and solidify your understanding of the different aspects of plate tectonics and how plate tectonics explains all the features that we see around us. It explains our mountains, it explains our oceans, and it explains the climate that we live in to some degree. It explains a lot of different important things to us. And as we move on to talking about the seafloor, we'll take a deeper look at some of how plate tectonics can explain the things that we see. Well, I hope you enjoyed this lecture. If you have any questions, please feel free to contact me. Enjoy learning.